After his PhD, he moved to Paris, where he did 2 years, 1 year, 2 years, 2 years postdoctoral stay in the group of Francesco Mauri. There he developed the stochastic self-consistent harmonic approximation, which is right now the cutting edge code to calculate anharmonicity, phonon anharmonicity in solids. And after 2013, he joined the IPC, and so at first as a postdoctoral researcher. And from 2015, he started as assistant professor at the University of Basque Country, and now is associate professor. Some of his awards, and so for instance, he got the starting grant in 2019 to work in the superconducting hydrides he's talking about today. And also he was selected by the editorial board of Journal of Physics Condensed Matter as an emerging leader, I guess in Europe or the world or Spain or the Basque Country. I don't know, it's emerging. Finalist of the 2015 Volk Heine Young Investigator Award, and so he got a Fundation postdoctoral fellows. So I guess every one of you know him. He's very well known here. He's trying to explain us as in a more or easier level the type of theory he does, the calculations he does, with a special emphasis in the high density superconducting hydrides and charge density within solids. So please, John, stage is yours.
Okay, thank you, Santi, for the invitation, and also to Marek, who I think he cannot be here, for considering me here for these community seminars. I think this is a very good idea, that we share our results in the different groups here with the local community. So I'm very happy to explain a bit what we do in the group. And basically, so yeah, as Santi said, we are doing theory, mostly ab initio calculations. And my goal will be to explain to you basically what we are experts on, or I mean, which is basically the treatment of quantum anharmonic effects in solids. And I'm talking about the ions, right? So quantum effects on the ions vibrations and anharmonic effects in the ions vibrations, right? So I will also present some of our results. I think I will cover the hydrogen-rich superconductors and the charge density wave materials. And maybe if I have time, also some other systems that we are dealing with. Okay, so this group is our group is in the CFM. Okay, this is the group here: Georgia, Jowen, Antonella, Diego, Martin, and Josu. This is the last picture. So we have some of them have left, but what I want to say is that I mean, much of the work that I'm going to present here is thanks to the group that we have at the CFM. So first of all, I want to talk about what I understand, or what are quantum anharmonic effects on the ions. I hope that this will be clear. Then I will explain the method that we developed to tackle this problem, this situation. And then I will move to some applications of these ideas. So first of all, I will talk about high density superconductivity in the hydrogen-rich materials. I will talk about the prediction and understanding of charge density waves, okay, which is something that we are working a lot. And then if I have time, how much time do I have? 45 minutes, Santi? I don't know. So let's see how we are doing with time. But maybe I'll talk about something that we are doing, which is very nice in graphene, an application that we are doing for graphene, which is related to how sound propagates in graphene and about its bending rigidity, which is a very old story that I think we have interesting results now. And something also very new that we are developing in the group, which is higher order electron-phonon coupling. And this is something rather new, and we are starting to work on that, but we already have some good ideas. So this is a typical picture of a solid, right? Where we have ions in a regular lattice, and then we have electrons that flow, right? A metal, let's say this is a metal, okay? But this picture is never true. So the ions are never static at their lattice sites, okay? They have to vibrate. And if not, the Heisenberg principle is not satisfied, okay? So we have even at 0 Kelvin, the ions fluctuate, they move, they vibrate. If not, we will know the velocity and the position of the ions at the same time. And this cannot be true. This is not quantum mechanics. So indeed, the general picture of a solid is something like that. The ions fluctuate, they vibrate, okay? So how we treat these calculations, how we treat these fluctuations, right? So the standard treatment that we are going to adopt, and we always work in this approximation, is the Born-Oppenheimer approximation, okay? So first of all, we need to, this approximation somehow separates the electronic problem from the ionic problem, somehow. And therefore, we first solve the electronic problem of the Hamiltonian, okay, which is basically the kinetic energy of the electrons, the Coulomb interaction between the electrons, the electron-nuclei interaction, and if you want the nuclei-nuclei interaction, which is just a parameter for the electrons, okay? And in principle, you have to solve that, okay? This defines an energy and a wave function where R, let's say R here, the capital R is a parameter that defines all the positions of the ions in the crystal. Okay. So what is the Born-Oppenheimer potential or the Born-Oppenheimer energy surface? Is the ground state solution of this. Okay. This defines the potential in which the ions vibrate. So from this ground state, we define the Born-Oppenheimer potential, and this defines our nuclei problem, the problem of the nuclei. Okay. We turn this potential into an operator. This is a trick that we do. Okay. And then we have the nuclei kinetic energy plus this potential, and this defines, if you want, the nuclei problem. Okay. Obviously, this is a very complicated problem. The electronic problem is very complicated because we have the electron-electron interaction and so on and so forth. I'm not going to enter in these details. Okay. And also, this is also a very complicated problem, even if we restrict to that, right? Because here, this is a R here is defines all the ions in the crystal. So this is a many-body problem as well for the ion problem. So we have two many-body problems, one for the electrons and another one for the nuclei, right? So the typical thing that we do, and many other people, is to use DFT to solve the electronic problem, okay? In which we substitute all the electronic problem by the Constant potential, right? And this defines a band structure and so on. And this has all the pros and cons of DFT that I'm not going to enter into detail. But this, once we solve the electronic problem in this way, we can have access to the Born-Oppenheimer potential, right? Still, this is tricky, okay? So the Born-Oppenheimer potential is tricky. As I said, it's a many-body problem, even if you calculate it with DFT or whatever, okay? Because the ions, you have all the ions in the crystal, right? It's a many-body problem. So you need to do some approximation. And the typical approximation is the harmonic, right? What we do in the harmonic approximation, we see which is the ionic configuration, okay, where the ions sit, and minimize this potential, okay? We look for the minimum of this potential, right? This will define this R equilibrium position, right? If this is so, then we can tailor expand the potential, okay, in terms of displacement from these reference positions, right? And we truncate the expansion at second order, okay? When we truncate the expansion at second order, this is basically the first order is zero because we have precisely expanded the potential at this position where the forces are zero, okay, if you want, classical forces are zero, the derivatives of the potential are zero, right? So basically, in the expansion, we have these force constants, okay, which are the second derivatives of the potential with respect to the displacement. If you want the Hessian of the Born-Oppenheimer potential, right? So this can be calculated by finite difference, it can be calculated by density functional perturbation theory, et cetera, et cetera. This can be calculated, and then you diagonalize this object, okay, and you get the phonon frequencies. And you can draw a phonon spectrum, okay, in the harmonic approximation. Okay, but this is the typical picture. But now let's try to understand what are quantum and harmonic effects, okay? So somehow this picture that I was mentioning, which is what most of the people are dealing with, is a classical picture, okay? Why do I call it classical? It's because, well, if we apply these ideas to, let's say we have this Born-Oppenheimer, okay, that I simplify, okay? The solution is, okay, I have, my positions will be here at the minimum, right? This is our equilibrium position that I would say, I would calculate the second derivative here of the potential, okay, the Hessian, this would be the force constant, and this would define the vibrations here of the phonons, right? So why do I say that this is classical? It's classical because the ionic positions go to the minimum of the potential, right? They are like balls, and these are balls that vibrate at the minimum of the potential. But as I said, ions are quantum objects, Okay, so they need to be described not as a ball, they need to be described by a wave function, right? So we need to describe by a wave function. Imagine that we can solve the Schrodinger equation for this potential. Okay, it could happen that the wave function that we find, the solution is this one. It could happen. So then what is our position? The position where the ions are, okay, they are fluctuate, obviously. But if I do X-ray, where I will see the ions? I will see them at the expectation value of the ionic wave function taken of the position of A, right? And this might be centered here, for example. Okay? So this is a quantum picture. And why do I say that quantum anharmonic? Because if I really want to solve this quantum position of the ions, I need to take into account the full Born-Oppenheimer potential. Okay? If I do a Taylor expansion of this potential here and stick to second order, even if I solve in quantum mechanics, I will get the classical solution. Okay? So we need, that's why quantum and anharmonic to me are, you know, the same thing. So you have anharmonic effects if you have quantum nature of the ions. Okay? If the ions, and this is true, they are like that. Okay? So one important thing, so if we want to treat a situation like this one, okay, so if we do, let's say, the classical picture, and instead of taking the expansion of the potential at the minimum, we do it at the position where the ions are, let's say the maximum of the, or the center of the wave function. Here, this solution will tell us that the system is unstable because the second derivative here is negative. This is concave, no? Right? Concave, right? So in this harmonic approximation here, the system will tell us, no, this is impossible. This will never be here, okay? So therefore, if we want to tackle these systems with strong quantum and harmonic effects, we cannot do perturbation theory. Because here, the perturbation theory would be something that you build on top of the harmonic solution. And here, the harmonic solution has no ground state because you have a concave potential. We don't have ground state. Okay, so we need to do something which is not perturbative, right? We need to come up with a variational theory, for example, to describe these situations, okay? And this is the sham method. The sham method is a variational approach, okay? So if we have a variational approach, what we need to is minimize the energy or the free energy if we want to take into account also temperature effects, right? So this is what we are going to do. We want to minimize the free energy of the system, of the system, right? So this is the exact problem. This is the Hamiltonian for the ions, okay? So this is the kinetic energy of the ions plus the full Born-Oppenheimer potential, full, no harmonic expansion, okay? The full one. What is the exact free energy of this system? So we should calculate the density matrix, okay, which is here with the full Hamiltonian, right? And then we calculate the free energy with the, let's say, the energy term plus the entropy term, right? The problem here is that this is a many-body object, this Hamiltonian, as I said in the beginning. So we don't know this expression. We don't know which is this partition function, okay, this density matrix, okay? So therefore, we can propose a variational problem. Let's imagine we take an alternative density matrix, okay, which is parametrized with a Hamiltonian that is harmonic in shape. The harmonic Hamiltonian that parametrizes our density matrix, okay? Okay, so we can parameterize this Hamiltonian with force constant, okay? But these are not the second derivatives of the Born-Oppenheimer potential. These are auxiliary force constant that parameterize this density matrix, okay? And some positions, this capital R, that I'm going to call the centroid positions, okay? And these are precisely where the ions, the wave function of the ions is centered. This is what they mean, okay? So what we can do is take this density matrix and substitute the true density matrix by this one in the calculation of the free energy, okay? But note that here, I'm not changing the Hamiltonian. So the full Born-Oppenheimer energy is here, right? So then we have this variational free energy, which is parameterized by these centroid positions and these force constants. And what we can do is, okay, let's minimize this free energy with these two parameters, okay? And we will have a good approximation for the free energy of the system, okay? And this is the idea of the self-consistent harmonic theory, which is not developed by us. This was developed in the 50s. We developed this with a stochastic method and so on and so forth, and bring it to the ab initio world. And we were able to do calculations with this theory, which is not new, okay? This is if you want, if you are more used to electrons, thinking into electrons, this is like a Hartree-Fock theory, but for the phonons. Why do I say so? What do we do in Hartree-Fock? We try to obtain the single particle orbitals, let's say single particle orbitals, that best describe the full electronic Hamiltonian without approximating the electron-electron Coulomb interaction, right? So here, this is similar. Somehow what we are doing here is we take a density matrix, which is described by a harmonic potential, and the harmonic picture is single particle for the phonons, okay? And then we try to optimize these single particle phononic wave functions, okay? So it's equivalent to Hartree-Fock for the phonons, okay? So this is the level of theory that we are doing, right? So just one example, okay? This is let's say this is a 1D potential, okay? This is the Born-Oppenheimer potential. And let's solve the energy here, okay? So the classical harmonic solution is this one, okay? The classical Born-Oppenheimer energy is here. This is the minimum, right? But then we need to calculate the second derivative here, right? Which will be rather large. And this will give us an energy for the phonons, right? If we sum these two terms, the total energy is this one, okay? If you solve the system here with numerical methods, this is easy to solve exactly. The exact energy is this one, okay? It's much lower than the harmonic classical solution, okay? When we solve the energy with the SHA has to give us, it's a variational method, so it has to be larger. You see, it's very close. It's a bit above, okay? And then what about the wave functions, okay? So this is the harmonic wave function, which is centered at this position. This is R0, okay? Where we have the minimum of the potential, right? And it's a Gaussian. The wave function is a Gaussian in the harmonic approximation for the phonons. Okay, the exact wave function is this one. Okay, it's not a Gaussian, exact. Okay, but the expectation value of the position operator is centered here. It's here. Okay, in this point here. Okay, so with our SHA method, we have this. This is our solution wave function. Okay, so you see, it's rather different from the true wave function, but still we have a very good energy, and also the position that we get. Okay, it's very close to the exact solution. So even if we have a rather crude approximation, Gaussian approximation for the wave function or the density matrix that I was describing before, okay, we have a good approximation also to systems which are extremely anharmonic and where the wave function is not exactly Gaussian, okay? So this is a bit the general idea. Yes, Thomas, yes.
Just a question. The previous slide, you had temperature, no, as the difference between the free energy. How do you choose the temperature? What is the role of temperature?
So here, this is zero temperature because I'm talking about wave functions, okay? And to make a simple example, but with temperature here, basically, so you can prove that this, so if you want, the wave function is the probability distribution function at zero temperature, okay? So basically, what we have is the probability distribution function at finite temperatures is also a Gaussian in our model. So it's basically a Gaussian. Right, so if you want so it's basically here the temperature enters in you have the temperature here. So the density matrix here and the probability distribution function that it defines, it's temperature dependent, and it's well defined in terms of also in the quantum limit and in the classical limit. So we have absolutely no problem with the temperature definition. It's exact, so it's correct. No, not exact, it's correct. I don't know if this solves the question. So, but basically in this idea, so it would be that here, so our wave function depends on the temperature somehow, okay? So we can do several things, because if you want to somehow go back here and try to obtain this position, right, you are somehow relaxing the structure considering these quantum anharmonic effects. So the atoms change. They are no longer necessarily in the minimum of the Born-Oppenheimer potential. It can be different, right? As in this case, right? So we are somehow relaxing the structure, okay? As you do in DFT, in quantum espresso, when you do relax, you get a structure, but we do it taking into account this quantum anharmonic, right? We also do it with the pressure, because we define the pressure, instead of calculating it classically, as a derivative of the Born-Oppenheimer potential with respect to a deformation, okay? We can calculate it from the free energy, okay? And in this way, we have access to a relaxation also of the cell, let's say the lattice parameters, taking into account this quantum anharmonic effect. Okay, so we can also do that, and we have a full relaxation. If you want, like those of you that use quantum espresso, it's like a VC variable cell relax, also taking into account not classical, but considering these effects. Okay, so we can do that. Okay, which are the phonons? I have not mentioned anything about the phonons yet. Okay, so far I have described a wave function that it has as a parameter some force constant. Okay, what are the phonons in the classical picture? The harmonic phonons are they come, as I said previously, from the Hessian or the second derivative of the Born-Oppenheimer energy surface calculated at the minimum of the Born-Oppenheimer potential. What is the analogy in our theory? The analogy in our theory is, okay, we calculate the second derivative of the free energy, okay, with respect to our centroid position, let's say where we place our wave functions, okay, at the position that minimizes the free energy, okay? And we have an analytic form for that. I am not going to enter into details, but basically it's just the auxiliary force constant. So the phonons that would come from this auxiliary force constant that we use as a parameters, plus some extra terms, okay? Some extra terms, okay? So somehow this is a clear analogy of the theory. Well, note, these are temperature independent. These don't depend on the temperature. These do depend on temperature, okay? Because our free energy depends on temperature, right? So somehow, and therefore we are capturing here all anharmonicity here. All anharmonicity because we are not doing any approximation on the Born-Oppenheimer potential, okay? We also have, but this is a static theory for the phonons. Phonons are dynamical objects. They have a line width, okay, due to the phonon-phonon interaction and so on. So we also have a dynamical extension of the theory. I'm not going to enter into details. So we have a self-energy defined, blah, 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 and so on. I'm not going to enter into details, but we can also calculate spectral functions of the phonons, which are what, for example, it's measured by inelastic neutron scattering or X-ray scattering, right? So you are measuring is a spectral function, okay? Right, so we have this dynamical theory, which actually is in principle we define it as an ansatz, but it was later proven that it's exact theoretically and it's well framed, okay? So this is basically the SHA theory in 3-4 slides, okay? So therefore we have access to full anharmonic theory from static to, we can do lattice relaxations with anharmonicity, get phonons, and so on and so forth, dynamical properties, and so on. So we have a school in June, so still we have some places to register here. So everyone that want to join, there are some still places, okay, to join. So let's move a bit forward. I speak very slowly. I'm sorry. Let's move to some examples on the hydrogen-rich superconductors of these ideas. Okay. So this is the evolution of the highest critical temperature in history since it was discovered in 1911. Okay. So basically, we have here the simple metals family, then the discovery of the cuprates in the 80s. Okay. But the TC has not been increased so far. Farther, let's say. Here we have the pnictides. This is controversial, this experiment. So I don't know whether I should put it here or not. But also no further improved. But in the last years, okay, it's getting more and more. So 8 years, okay, at high pressures, hydrogen-based superconductors were discovered with critical temperatures above 200 Kelvin. Okay, so this experiment is controversial. It was retracted from Nature, and also there is a new experiment that is also very controversial, published 2-3 months ago in Nature as well, of the same group that claims that they measure room temperature superconductivity at only 1 GPa. Okay, but it's a very controversial experiment. Okay, they've been well, you can ask me about that. But these others, lanthanum H10, H3S, and all these other points that I put here, they have been reproduced by different experimental groups. Theory, as I'm going to show, is consistent with these discoveries. So my opinion is that these are really good experimentalities, and this is true. Okay. So, for example, we have done calculations in one of them, lanthanum H10, well, several of them, but this is the lanthanum H10 story. It really illustrates the role of quantum anharmonic effects and how important they are in these systems, okay? So here, one approach to discover this material was crystal structure predictions, okay? What is crystal structure predictions? It's like people take a stoichiometry, and try to look for the compounds at a given pressure that have lowest enthalpy. Okay, this is it was very developed in the early 20,000s, no, 20 years ago, and it's been crucial to discover these compounds. Okay, but if you do this crystal structure prediction, these are classical, so they work in the Born-Oppenheimer energy surface. Okay, so when you do that, you find like this kind of distorted structures. Okay, they are distorted. Okay. And they are distorted versions of this high symmetry structure. Okay? They have much lower enthalpy than this pressure. Okay? Actually, in the experimental pressure range where this material was found to be a high TC superconductor of around 250 Kelvin, this structure is not the minimum in the Born-Oppenheimer energy surface, right? These others have much smaller energy. But experiments are stubborn and they find precisely this high symmetry phase. Okay? Down to at least 130 GPa, okay? So it's basically 100 GPa below where these structures are not found in the calculations. Experiments tell you that it's still this high symmetry phase, okay? This is what experiments tell you. So actually, what we did is, okay, is this related to quantum anharmonic effects? And indeed it is. So we took this distorted structure as an example. We took several, but this is an example. Okay, it's a rhombohedral structure which has 4 different Bykov independent parameters. So we started with this structure and we did a sharp relaxation of the structure. Okay, also variable cell because we are changing the angle of the rhombohedral angle, right? And as we evolve in the minimization, this angle goes to 60 degrees, which is what you have in an FCC description of the lattice. You can describe an FCC as a rhombohedral lattice with 60 degrees, right? In the primitive unit cell, okay? And the Bykov positions evolve into something that precisely matches the FCC Bykov positions. So what we are seeing is that this structure is changing into this structure thanks to quantum anharmonic, okay? So we started also from a different point, at a completely different structure, one of the others predicted by a classical crystal structure prediction, and we also ended up in this crystal structure. So what does this mean? This means that classically, you have several local minima, right? Where you have several different structures, but when you go to this quantum energy landscape, all these minima are washed out, and you have just one minima, which belongs to the high symmetry. Okay, this is what it means. So somehow these quantum anharmonic effects have a huge impact on the structure, right? Also on the phonons, obviously. So if we look at the phonons of the high symmetry phase, okay, below, let's say 230 GPa, we have instabilities. So let's say the second derivative of the Born-Oppenheimer energy surface it's concave for many distortions. This is what this means, phonon instabilities, negative phonons for us, okay? So let's say for many type of Qs, many type of possible distortion, we have distortions that lower the Born-Oppenheimer energy surface. This structure is not a minimum of the Born-Oppenheimer energy surface. This is what it means. But on the other hand, when we calculate the phonons from the free energy Hessian, second derivatives of the free energy, okay, including these quantum anharmonic effects, this structure is stable, the high symmetry phase. So it is a minimum of the free energy landscape that includes these quantum anharmonic effects, right? And obviously, with these phonons, we can do superconductivity, we can calculate superconductivity, and so on, right? So this is basically the calculation we did with different theories of superconductivity. Okay, I will not enter in these details, but with these phonons, we can calculate this critical temperature, do superconductivity in theory, and so on, and we get a very good agreement with the okay. So one remark here that I think it's important to understand a bit this role. Why this system has such a huge harmonic phonon instability, okay? It is because of the huge electron-phonon coupling in this system, okay? And this is known. The electron-phonon coupling is a destabilizing force in a material, okay? So if you have a large electron-phonon coupling, okay, the system wants to distort, okay, to reduce the energy, okay? And this is what happens in the electron-phonon coupling. So this is the harmonic phonons, and you can see here what we have. These are the harmonic, the dynamical metrics, if you want. These are Kohn-Sham states, okay, Ij, and what we have here are the electron-phonon matrix elements, basically. Okay, so if the electron-phonon matrix elements are very large, and this is negative definite, Okay, this part, this contribution to the dynamical metrics. Okay, so the phonons will be lower. Okay, so somehow this is a message. Okay, that's why we have. This is the same as hopefully I will speak later about charge density waves. It's the same story of charge density waves as well. So what is a charge density wave? It's a breaking of the symmetry that lowers the energy, and this lowers the electron-phonon coupling when you go to the distortion. Okay, distorted structure. This is illustrated also here. Okay, here I plot the density of states of the high symmetry phase and some of the classical structure that you find in the Bohr-Oppenheimer minimum for this compound. Okay, when you create a distortion, this density of states at the Fermi level is lower. Okay, here at 11%, here at 23%, depending on the distortion, right? So the message here is that thanks to quantum and harmonic effects, this high symmetry structure with a huge electron-phonon coupling is stable. Okay, so somehow quantum and harmonic effects can make thermodynamically stable structures with a huge electron-phonon coupling. Okay, that if we restrict to classical picture of the ions would not be stable, and this is the important message. Okay, so actually we know that when we go to and actually you can see here in the experiment. Okay, here in the experiment, when you go to the when you reduce, you go to the lower symmetry phase experimentally, the TC rapidly goes down. So somehow, before, in all this pressure range, 100 GPa above here, from here, this high TC is kept thanks to quantum and harmonic effects. So somehow, I believe, and this is the conclusion of this part, let's see, let's go forward. Okay, this is H3S. So these similar things we have seen in different compounds as well. Okay, so somehow this is the message that I want to give here. Ionic quantum effects have a huge impact on superconducting hydrides, and high TC structures can be stabilized at much lower pressures than expected classically. So somehow, if we want to find high TC compounds in these families, we really need to consider these effects, because this effect will make stable structures at much lower pressures than predicted classically. Okay, so I think it's very important to consider this. Okay, so is there any question, or shall I continue? Maybe. Yes, go ahead.
Yes, thank you. I need to know if the quantum and harmonic effect has impact on the gap of the structure.
The gap of which gap?
The band gap you show.
The band gap. Sure, it does. Yes. Yeah, it does. So somehow. Here we see in the density of states, right? So somehow you see that you can keep a high density of states, okay, by considering these effects. If you distort the structure, this is lower. So somehow you are opening gaps. Okay, this is not an insulator. It's not a metal insulator transition, but effectively you are opening some gaps when you distort, right? So it has an impact on the electronic structure. Yes, yes. Okay, so let's move to charge density waves. Okay. I mean, when I started reading in my PhD thesis what a charge density wave, I was terribly confused, because charge density wave. To me, the problem was wave. Okay. What the hell is a wave? Is something dynamical that moves and propagates in time, right? But then, right now, after I don't know how many years, I'm convinced that a charge density wave is a thermodynamic phase of a solid. It's something thermodynamic. It's not something dynamic. It's something thermodynamic. Okay. What is the story? Okay. This is the classical picture of a charge density wave. Okay. We have a lattice with this periodic repetition of atoms, and we have, imagine this is a free electron gas, and the density is homogeneous. Okay. This is a picture at high temperature above the charge density wave temperature. Right. So if this is true, okay. If this is a thermodynamic state, it means that above the charge density wave temperature, the free energy of the charge density wave phase is higher than the free energy of the high symmetry phase. Okay. Then when we go below the charge density wave temperature, we have a lattice distortion and we have a modulation of the charge, electronic charge. That's why it's called charge density wave, because we have a modulation of the charge, but this modulation is static. Okay, it's just a modulation of the electron gas, nothing more than that. Okay. So when we go to this case, the charge density wave, the free energy of the charge density wave phase has to be smaller than the free energy of the high symmetry, because it's a thermodynamic state. Okay. So when I understood this, to me, charge density wave were clear. Okay. So when we have a charge density wave transition, normally we are talking about second order phase transitions or transitions that are very close to a second order phase transition. Okay. What is the difference between a second order and a first order phase transition? Okay. So when, well, I don't know whether I should call here charge density wave temperature, but whatever. So when we are below the charge density wave temperature, we have a minimum of the free energy in the low symmetry phase. So Q somehow here is the order parameter we have, which basically measures a distortion of the ions in the lattice. Okay. Okay. So when Q is equal to 0, we have the high symmetry, high temperature phase, and when Q is different from 0, we have the low symmetry phase, charge density wave phase, if you will. So when we increase the temperature, okay, it can happen that we have still a minimum here for this high symmetry phase, but already the low symmetry phase, but already the high symmetry phase becomes the minimum. Sorry. So then, if we plot the order parameter as a function of the temperature, we'll have a jump here. Okay. This is if it is first order. If it is second order, this minima that we have at low temperatures disappears exactly when we go to the high symmetry phase. Okay, so this is a second order phase transition, and therefore the order parameter is continuous. Okay, sometimes there is a narrow border, and there is a small jump here, and in these cases we have a weakly first order first transitions, right? And so some charge density waves are claimed to be weakly first order as well. Okay, but basically I'm going to describe mostly this second order phase picture, right? So if it's about calculating what happens here with the free energy, right? So we have a perfect machinery with the SHA to calculate that, right? Because basically, if it is a second order transition, basically when the charge density wave happens, it happens when this derivative here, this second derivative here, becomes negative, because at high temperature, if this is the minimum, in the high temperature phase here, the free energy will be convex, right? So all the eigenvalues of the free energy Hessian will be positive. Okay, but when we go to the low temperature phase, okay, there will be this curvature here, okay, will become negative, at least for a given distortion, for a given Q. So we will have an eigenvalue that is negative in the free energy Hessian forms that I was describing in the SHA, and we get with the SHA, right? And I said we have this equation, so we know we can calculate these things, right? So precisely this is what is seen experimentally. So experimentally, for a second order charge density wave, they see how do the phonons depend? They collapse. Okay, so this is an niobium diselenide bulk, and as you can see here, this is at high temperature. When you lower the temperature to 50, the phonons come here, and at 33, which is the charge density wave temperature, the phonons are measured to be basically 0, right? Here you see a sum of the frequency dependence of this phonon mode. Okay, so it goes to 0. Okay. Actually, so we can do that as well with these calculations, but let me be clear with one statement. So what melts a charge density wave phase? Okay, so if we at t equals 0, we have a structure is in the charge density wave phase, a distorted phase, let's say. What melts it when we increase the temperature? Entropy, right? It's entropy, because there is no other ingredient in the free energy that would enter. So it's entropy melts a charge density, right? So let's say that we calculate the free energy, okay, considering this is let's say, the energy, okay, this is the energy calculated with the SHA. This is the entropy coming from the ions, which is the one that we include in the SHA, okay? But here we can also have an estimate of the electronic entropy, the entropy part that comes from the Fermi-Dirac occupation of the electrons, okay? Right? So let's say we just calculate the phonons, neglecting, so from let's say the harmonic part, this is the harmonic, plus the electronic entropy, okay? We calculate in this way. This is for niobium diselenide bulk and monolayer. So you can see that indeed, the charge density wave, let's say the phonon instabilities disappear, but they disappear, I don't know exactly the temperature, but around 1000 Kelvin, okay? Around 1000. Good. So yeah, electronic entropy melts the charge density wave, but at 1000 Kelvin. Experimentally, it's 33 Kelvin. Okay. What happens if if instead we don't consider the electronic entropy and we calculate basically what we calculated in the shell, considering the ionic entropy. Okay. Then the charge density wave melts, but in our calculations between 50 and 100 Kelvin, so much closer to the experiment. And actually these are phonon modes measured experimentally, and we are in rather good agreement. Okay, here we are overestimating a bit the transition temperature from 33 to around 70, I think. Okay, but I mean, I think this is a rather good agreement for this type of calculations. Okay. And also, this is just for Miguel, that in the bulk and monolayer, we get a charge density temperature which is very similar, because there is controversy about that. So I mean, we are in agreement with his measurements. Well, so then we can have access to charge density wave physics. We can predict when it happens and when. So the first message is that entropy, ionic entropy, is the one that melts the charge density waves. Okay, not electronic entropy. So this is niobium diselenite, an example. Okay, where basically here in the harmonic approximation, you see that the system is unstable in the bulk, so it should have a charge density wave, but it does not experimental. Okay, and even if you go to even if you go to 0 Kelvin with our SHA calculations, we don't have instability. So we see that somehow here quantum effects prevent the charge density wave. So there is no charge wave thanks to these quantum effects. Okay, and the phonons we get are in very good agreement with the experiment. But it's interesting here. So if we go back to the monolayer, there are controversial results. Some say that there is a charge density wave, some others say there is no charge density wave. It might depend on the substrate, it might depend on the electron doping, and so on. But it's interesting that with only a 0.5% of tensile strain, we can see that a charge density wave emerges. So some phonon instabilities appear. Okay, so a tiny strain can induce a charge density wave in the monolayer of niobium disulfide. Okay, somehow, so we can have access to this physics also, how a strain impacts the charge density waves and so on. Okay, this is the one of the latest results we obtained with. Tell me.
There is a question.
There's a question. Yeah.
Yeah. So this strain is uniaxial or?
No, this is a homogeneous strain.
You get the 3 by 3.
So it's 2 by 2. It's a monolayer, so it's a 2 by 2. Yeah, strain.
Yeah, but the charge density wave is 3 by 3, as you get also in this. Right?
But this is a monolayer. So this is a monolayer. This is the monolayer. Sorry.
Yeah, I know. Yeah, but 3 by 3, I mean that you triple the initial in each direction when you apply.
Yes.
Okay. Yes, I see. Thanks.
Yes, but here we are also always working here from the high symmetry structure. So somehow we are determining the charge density wave from the high symmetry structure. Why? Because it's much cheaper for our calculations because we have much more symmetries. So we are somehow accessing the charge density wave from above. Okay, somehow. So from above, let's say. Okay, so this is a result that we obtained with Santi, our moderator or chairman. So here it's vanadium diselenide bulk in the 1T phase. So he measured the phonons with inelastic X-ray experiments, and we did it with these calculations, and we obtained a rather good agreement. Okay, and also so this is the charge density temperature that we get here, and this is the experimental one. And one thing that is interesting is that here we realize that van der Waals interactions, when we were including in the Oppenheimer potential, van der Waals forces were important to determine this charge density wave, for example. Okay, so it's something that it was unexpected to us because we didn't do that, and we were impossible to melt the charge density wave. When we included van der Waals forces, we were able to have a rather good agreement. So somehow we can also play later on the level of how we calculate the Oppenheimer potential that enters in the SHA calculations. We can see which are the important effects here in the charge density wave physics. Well, I'm going to skip that. So some messages. Charge density waves are melted by ionic entropy, or I think this is a statement that we can really be certain of, and that the strain can induce charge density waves. Also, we have done calculations in other systems. Also, electron doping suppresses the charge density wave temperature. And in most of the cases, I didn't speak about that. So I think we are already running out of time. the electron-phonon interaction is the main driving force of these instabilities, and not the nesting scenario that many people claim. And this is consistent with the picture that I was describing on the high TC hydride. Somehow, the high TC hydrides want to distort to lower the electron-phonon coupling. And here also, the electron-phonon coupling is large for these particular Q points that drive the charge-density wave, for these modes that drive the charge-density wave as well. So somehow it's consistent with this idea that the electron-phonon coupling is the stabilizing source of the crystal structure. Okay, that it's rather general. This is not something that we have come up with, of course. So I don't know, Chairman, whether I should go on or. So maybe I can just briefly talk about something a bit different. Okay, to change a bit gears, which is graphene. Okay, maybe I will skip the sixth part. Okay, this one maybe I will skip. So it's graphene. There is something fun in graphene. Okay, so graphene, and not only graphene, all 2D materials and membranes have an out-of-plane phonon mode, which is not acoustic mode, which is not linear. Okay, it's quadratic. Okay, so you see, this is the out-of-plane mode of graphene, and it's this dispersion, acoustic one. It's not a linear like the others, it's quadratic. Okay, and this happens for all 2D materials. Okay, this acoustic mode is the one responsible for the ripples that appear in these kind of membranes. Okay, like this kind of ripples. Okay, so this creates problems. Okay, so let's say we calculate the phonon lifetime or line width. Okay, in the harmonic approximation and perturbation theory, right? So you take this harmonic calculation, which is, this is a harmonic calculation, okay? So this Q square behavior is a harmonic result, okay? This is a result in the harmonic approximation. So if you do perturbation theory and harmonic perturbation theory on top of this result, the line widths that you obtain for the other in-plane acoustic modes, you see the ones that go in plane, okay, do not vanish at Q equals 0. So this makes no sense, because this means that graphene cannot propagate sound in plane. Because if they have these phonons have a lifetime that doesn't go to 0, it means that they decay before doing a vibration in the really long wavelength limit. Okay, this makes absolutely no sense. Okay, so this is a completely unphysical result. Okay, this cannot be the case. There must be something wrong. Okay. So the classical solution to this problem, okay, is that somehow anharmonic effects linearize the dispersion of this out-of-plane mode. Okay, so instead of being Q to the second, it's a bit lower. Okay, it's a parameter Q eta, where this eta is a bit it's between 1 and 2. So it's not linear, but it's closer to linear, right? What does this mean? This means that the bending rigidity, let's say how much energy you need to put to bend graphene or any membrane, so this is any membrane, okay, diverges. So if this is true, the bending rigidity is basically the dispersion of this out-of-plane mode divided by Q squared. So if this is true, in the long wavelength limit, this diverges. So if this is true, this diverges. So what does this mean physically? That if I have a graphene sample and I put a one bigger, the bending rigidity is different somehow. Okay, so if this is true, this is the implication. Okay, and this is a bit weird because experimentally, okay, there are some experiments that have measured different independent experiments on graphene that have measured the bending rigidity, and they come up with a consistent pattern. So to me, there is also a problem with this as well. Okay, and this theory, I mean, this typical classical picture comes from much before graphene, because this is a problem that appears in all membranes. So this is a problem of all 2D material or 2D membranes. Okay, so it's an old problem that has been tackled a long time ago. Okay, basically with membrane theories, mostly with membrane theories, classical membrane models. Okay, so why do we expect a Q square dispersion for these out-of-plane modes? It's a symmetry argument, okay? It's because, okay, if we take graphene and we make a rotation like this. Okay, now graphene we look at on this, like we take an out of plane rotation. Then the Born-Oppenheimer potential has to be invariant, and this, including the fact that this is a 2D system, implies that precisely these derivatives go as q squared. So this is well known. Okay. What is the remark that is important that has been, I don't know, forgotten or not realized thus far? That if anharmonic phonons have to come from the Hessian of the free energy is also invariant to rotations. So therefore, the anharmonic phonons that I'm describing that come from the free energy Hessian, okay, have to go also as q squared. Okay, so this completely contradicts all the classical picture of how this problem is solved, because we are saying, according to this simple symmetry argument, it has to be q squared. Okay, so we have done calculations with the SHA, with empirical potential, and precisely this is what we see. So okay, I didn't put the label. Sorry, my mistake. So this is the harmonic phonons. Okay, you see I plot the frequency of the out of plane mode divided by q squared. So this flattens out in the harmonic approximation when we go to lower q. Okay, and the green is the free energy Hessian phonons. They also flatten out. So here we are saying it's q squared, and this is temperature independent. Also at 300 Kelvin is also q squared. Okay, so somehow this is the SHA result is consistent with the simple symmetry argument that I was presenting. Right. So we did that also with a membrane model, like those that were used in the 90s and 80s to explain these membranes, and we also get the same result. Also, it is q squared. Okay. Once we do, but one important thing, even if we have a q squared dispersion coming from the free energy Hessian, we can explain the problem with the sound propagation, because right now in our SHA theory, the line width of the full width of this out of plane, the other in plane occulting modes decays with q, right? There is no problem. So sound propagates despite we have a q squared dispersion. There is no problem, and this is thanks to anharmonicity somehow. I know this is complex, but there is no problem. Okay. So, but what's the story? The story is that in the old calculations, they were using these membrane Hamiltonians. Okay, they were neglecting this part, which is indeed it is small, but if you neglect this part, your Hamiltonian is no longer rotational invariant. Okay, actually, when we neglect this part and we do the same machinery, we get these phonons. I think it's it's the green this one. Okay, so you see you have divergence, so it's no longer flat. So therefore, this is consistent with the previous pictures. The bending rigidity diverges when you go to the q equal to 0 limit. Okay. But this is a result that appears because you neglected this term. If you include this term and you have Hamiltonian that is fully rotational invariant, then this flattens out. Okay. So this contradicts the full theory that was presented before classically for graphene and all membranes. Okay. So we have a completely different idea. So and it's very interesting. So because what people are always talking about here is about the how these things are presented. Are they presented by the calculation of the height correlation function? Okay, and the classical picture is okay when you go to the very long wavelength limit, you have a dependence that goes as q minus 3.2 or something like that. This is actually the real value that it's given in the classical theories. Okay, so we recover precisely this exponent when we have a non-rotational invariant membrane. But when we have a rotational invariant membrane, we have q to the minus 4. So we believe here that in consequence, okay, that the classical interpretation that the bending rigidity has to diverge in the long wavelength limit is not correct. Okay, so somehow the amplitudes are bigger, the bigger the sample, but the bending rigidity is the same. This is our interpretation of this story. Okay, so in conclusion, out of plane acoustic modes have a quadratic dispersion. Okay, but this still allows the propagation of sound. Okay, so I think it's I think I am very happy with this result. We've been struggling to publish this, but I am very happy with this result. I think I should stop here. No, so I will skip this part. Yeah. So basically, just to say that quantum harmonic effects on the ions are very important and give rise to very interesting physics. Thank you for your attention.
We have now some time for questions before the pictures. First is HR.
I have a very basic question that maybe even a bit stupid, but so how can you define one structure starting from the block theorem if you have an harmonic effects in the lattice?
But you're talking about electrons or
About whatever, let's say, I mean, you're sort of assuming that the periodicity will not be perfect, right? So
no, I'm keeping the periodicity perfectly of the lattice. So yeah. So the
atoms move anharmonically. That means that in any instant of time, the lattice will not be perfectly periodic. That's how I see it, or I mean, there may be a flaw in my
it is true, but let's say your average position,
okay,
your average position has the lattice periodicity. So then you have the X-ray. So what I'm saying is that, okay, I don't know, maybe it's going to take a while to go back to the, but so it's basically that what it has the periodicity of the lattice. It's not the position, it's the average position. So the average position of the ions do have a periodicity of the crystal and this, all the translational symmetry, if you want. So all the symmetry arguments that we use have to be considered not for the wave function itself, but for the center of the wave function.
So then the flaw in my argumentation is that when you do advanced structure analysis of a phononic system or phonons, the block theorem applies different, let's say based on averages instead of based on compositions.
Right. Yeah, that would be, yeah.
How does your approach deal with phonon lifetimes? Because you have harmonic, and if they are harmonic, then they are not interacting. So do you have to take a next step to be able to do this?
Yeah, I said that, yes. So basically, this is the extension of the dynamical extension of the theory. I went very fast on that.
Yeah.
But yeah, basically it's this. So we can calculate this Green's function is the displacement correlation function, which is what you measure experimentally with inelastic diffraction experiments. So basically, this is a dynamical theory. So here we can plot these spectral functions are calculated, and these are the lifetimes of the peaks, if you want. So we can calculate these lifetimes perfectly. So there is no, we have the calculation of the lifetimes. And even I think, I don't know if this is an example, but sometimes, so we can actually calculate these without approximating to alloration. So we can actually see line shapes that are complex that actually appear in some systems. Like in lead telluride, you have a double peak where you expect one peak, and it's not because there is a phase transition, it's because the harmonic effects are so big that this peak splits in two. So in elastic experiments, you should see two peaks instead of one, but there is no symmetry breaking. It's just because the Lorentzian shape is no longer true, and you have what we usually call like a potato mode. Okay, so so and we can actually have access to these things as well. Yeah.
And how different in general, well, this is a very generic question, how different are the gammas that you calculate from this spectra from the ones you would calculate traditionally with a perturbative? Are these?
It's system dependent. So if the perturbation theory works, I mean, our theory in the perturbative limit matches with the perturbative theory. So the good thing about our theory is that if we go to the perturbative limit, we have the perturbation theory. So somehow its perturbative limit is correct, which is a relief. It's like, okay, so if we go to the perturbative limit and harmonicity R is small, we have the perturbative solution. So if the system is perturbative, we have the same answer. If the system is non-perturbative, obviously the perturbative solution is wrong.
Thank you.
Have you applied your approach to ferroelectric materials?
Some, yes, yeah, but it's we are doing some calculations. Yes, Diego, where is Diego? He left. Yes, so yes, it's obvious that for ferroelectrics are like a charge wave, but for non-metals. I mean, so it's the same story. Yes, it's an obvious.
This is due to anharmonicity.
Sure. Yes. Yeah. Yeah, we have not worked so much on those, but yeah, I don't know why, but because we come mostly from interest of superconductivity, but yes, ferroelectrics are clearly.
Now magnetic electrics are.
Yeah, actually, this code is free and people have started to use it. So, and actually there were applications on strontium titanate and things like that with this machinery, and they got very good agreement with rather good agreement with experiments and so on. Yeah, with the transition temperature, let's say.
So I have two questions. So one, I'm thinking about Moirés and amorphous systems, and I think that there maybe anharmonic effects can be important. Do you have some intuition about it? Also, I mean, also there the lifetime of the phonons, when you go to zero, it doesn't. So it's not. You have a finite lifetime at q equals 0. I think there is different from this other case. But yeah. So do you think that this could be applied to these systems?
You are thinking about what Hector and so on are.
In this direction, yeah.
Yeah, honestly, I have problems to understand all these things. Huh? So
Yeah, it's not easy, but
I have problems to understand all these things. Yeah, but how can you have a quasi-particle that has no energy and has a lifetime? To me, this is something that
yeah. So I'm asking, maybe the anharmonic effects are important, and you can.
I'm not sure, but these kind of systems. Okay, so. Always we have worked with atomistic approach, okay? So mostly DFT, and if we are doing DFT, forget at all about these systems, or with machine learning potentials or something like that. This, if you want to go to these systems, also forget. So they are too big for this machinery. So then it's true that we did it with a membrane model. So if you can come up with a membrane model or things like an analytic model, you could apply this theory as well. But yeah, I don't know. I cannot say much here. Yeah.
And then the other question is about your last part that you didn't say. I guess that this nonlinear electron-phonon is going beyond the Froelich model in a way that you.
Yeah.
So
if you are curious, you are curious about these things.
I mean, in the future I would like to. Yeah.
So. Basically, I can present the first. I only have 3-4 slides, so this is going quite slowly. So it's basically when I always present the resulting superconductivity and so on, right? So what we were doing, okay, what we were doing is basically this is the standard electron-phonon Migdal self-energy term, right? So here we have electron-phonon vertex, okay, which involves, let's say, well, there is another electron coming here, it's 2 electrons and 1 phonon, right? So this is basically the derivative of the potential taken with respect to the displacement sandwich between 2 electronic states, okay? This is this vertex, okay? So what we are doing so far in the hydrate and so on, we are renormalizing this phonon leg, okay? What we are putting the anharmonic phonon. This is what we are doing so far. But, okay, this was a question we had. Okay, is this contradictory to treat the phonon at an harmonic level without doing any approximation to the Born-Oppenheimer potential and the electron-phonon interaction, cut it at linear level? Right? It sounds like a contradiction, right? So that's why we started thinking about these things more. And we came up with a completely new theory. So let's say if you see here, so basically we have a theory where we approximate this self-energy right now. So let's say the electron self-energy is all these terms, all these Feynman diagrams somehow. So and we can calculate those ab initio. So it was very hard work. Okay. So somehow you are going beyond the Froelich Hamiltonian is just this term. So we have then a sum of all these infinite diagrams. These are not all the diagrams that you can have, but it's an infinite sum of diagrams. And we can calculate that. We can calculate those ab initio. So we can include those. And actually we were surprised. So just that, for example, the higher order terms are important, for example, in palladium hydride. In this superconductor, palladium hydride is a superconductor at 10 Kelvin at ambient pressure. Okay, it's one of the first hydrates that were discovered in the 70s to be superconductor, and these effects are huge. Actually, the electron-phonon coupling constant is doubled by this nonlinear effect. So I think there is lots of path here to, I mean, this is just the beginning of the story. So this is a work in progress, and I don't know where this will end up. But it seems that these effects can be important. In this compound, they are for sure. But I still don't have an intuition to say when these are going to be important or not. I don't know.
Yeah, I have a very quick question. So can your method be easily applied to molecules? I mean, is the periodic boundary condition a must in the method?
So our bottleneck is, if you want to, I didn't mention how we do this calculation. So basically we do this calculation. So we need to do this variational minimization, right? We do that by working in supercells, okay, and calculating forces, energies, and stresses for these configurations, random configurations that we create according to our distribution function. In the end, this is the bottleneck. So our bottleneck is the DFT calculation of these forces in these structures. So in molecules, which are 1D, normally it's much better. It's because you can go to bigger systems without because you just increase the dimensionality in one direction, right? So
no, I mean 0D.
Yes, for sure. Yeah. The problem is the number of atoms. So if your molecule is not too big, so yeah, we can do it. So normally, if we are doing DFT for the supercells that we are dealing with, I would say that maximum we can be talking about hundreds of atoms in the supercell. Okay, hundreds. This is with DFT. If you have a machine learning or a force field, you can go to bigger orders of magnitude of the number of atoms that you deal with this machinery. Yes. So bad molecules, there is no conceptual problem. No.
So quick question about your statement on the importance of electron-phonon whenever you have unstable modes. So say I get some computation harmonic phonon branches and 2 or 3 of them appear unstable. I'd like to understand, so you said it seemed to me that your statement was quite general, saying this is due to electron-phonon. I would just try like you to say a few words on that, like, I don't know, is this regardless of the type of phonon? Is it regardless of the type of electron? Is it in a metal? Is it in an insulator? Is there a but? Like if you have this type of system, this does no longer hold and so on.
Yeah, maybe I was too general in my statement. Yeah, I was thinking more in terms of these high DC hydrides, okay, where the electron phonon is very large, and also these charge sensitive wave materials, transition metal dechalcogenides mostly. And okay, Martin is calculating in the Kagome, and also it seems that it's similar as well. I guess you need to do. Yeah.
So it's more like whenever you've encountered this type of say instabilities at the harmonic level, it seems to be from electron-phonon origin.
I'm not so sure completely because you have the ferroelectrics as well, where I'm not so sure whether these claims I mean you calculate the phonons for the ferroelectrics.
Yes,
you have huge phonon instabilities, and I don't know whether you can really talk about electron-phonon coupling there, or it's more something chemical if you want. I don't know. Maybe I would say for the charge sensitive waves in metals, in all the cases that we have done calculations, it seems that the electron-phonon is the driving source of the instability in these high DC hydrides as well.
And this would be electron, when you say electrons, you're thinking about the Fermi electrons, like the ones in the Fermi state.
Yes.
Okay.
Yes.
Not some low laying or
no. But this is true that maybe you could export these ideas in insulators to something like that. Yeah. Right. Yeah. But I have no intuition about that.
So any further questions? There is nothing online. So I also have a couple of comments. Can I ask you questions?
Of course. If you're not hungry,
I am starting to. So my first is related with what our last question. Your assumption point is there is always a sizable electron-phonon interaction. What if a charge density wave is driven by nesting? The divergence of the electronic susceptibility. Can you calculate the onset charge density?
Yeah, there is absolutely no problem. So it's not an assumption that I'm doing. So actually, this is a result that we need to analyze later. So because as we are calculating the free energy, the electronic susceptibility enters in this free energy. So it's there. So there is no. So we have all effects if you want. All nesting effects. If nesting is the source of the electron-phonon so of the instability that appears in the calculations as well. Then later you need to do, search for the origin on other signatures somehow. Okay, so but it's not something that I am assuming. Okay, so if it's a different scenario, it will come out as well. Instability will come out.
Okay, and the second question is how good your SHA code is calculating something which is some thermodynamic property which is anharmonic, like thermal conductivity.
Okay, thermal conductivity is not a thermodynamic variable; it's a transport thing.
But it's what I call thermodynamic property.
Yeah, so it's so actually we are doing calculations. So in team selenide, for example, we did the calculations of thermal conductivity. So for thermal conductivity, you need several things. You need phonon spectra, and you need phonon lifetimes mostly. This is the two ingredients that you need. Okay, so we have those in the theory, as I explained. So we have phonon spectra and lifetimes. Okay, so yes, in principle, I mean it's good. Then you have other type of theories of calculating the thermal conductivity, but I'm not going to enter into detail. You can just solve Boltzmann equation in the simplest approximation, or you can do more complex Kubo based on Kubo formulas or so on. But in the end, the ingredients are the same. So in systems where the harmonic approximation gives you unstable phonons, you cannot do the standard perturbation theory to calculate thermal conductivity, and you need to go to these machineries or similar things to do this kind of calculations. And that's the case that we did in team selenide. We did this calculation, for example, at high temperature, in the high temperature phase.
Can I maybe quickly comment on your first comment?
Yeah.
Or the answer you gave? I mean, strictly speaking, you have all the ingredients except the electron-electron interactions, right?
Right, the electron-electron interaction.
Yes, so I was wondering, I haven't followed this literature of these materials and so on. I wonder whether any DMFT and these types of approach have been used to compare really with your approach, which is very robust from the ionic point of view.
Yeah.
And then not just nesting, but you would need the electrons are actually interacting. So I wonder whether there is any study comparing those two.
Okay, so basically we treat the electrons at the level at which we treat the Born-Oppenheimer energy surface. So we could do it with, if this Born-Oppenheimer energy surface is treated at the quantum Monte Carlo level, we would have all correlations included. If we have at the LDA level in DFT, so the correlations of the electrons would be treated at that level. So in that sense, the machinery is somehow independent of what happens to the electrons. This is true. In most of these cases, it's true that we were working with DFT at a level which is PBE or standard DFT. This is true. But I think the problem is there. So it's not in this machinery itself. It's on how you are including the Born-Oppenheimer energy surface. So you will need to go to higher orders. In the hydrides, I mean, in the hydrides, superconducting hydrides, I think Tomeu Monserrat has done some DMFT calculations, and the effects are not that strong. So actually, you change the correlation, the DFT exchange correlation in these hydrides, and the results are rather consistent. And they are more consistent when you go to the anharmonic result. So somehow the results depend less on the functional when you go to the anharmonic results. And to me, this makes sense. Because somehow when you are fluctuating the things, somehow the small subtleties at the Fermi surface are somehow washed out. Somehow. I don't know if, well, we could talk about that, but.
Okay, no further questions. So let's thank the speaker. I have to remind you that there are pinchos now. The kitchen.
Yo tengo el modelo es un modelo continuo que tienes básicamente la respuesta elástica, si es un modelo continuo si fuera de membrana y la fuerza de banda. ¿Podría ahí aplicar tu formalismo?
Sí, pero tienes que pegar de un trabajo analítico para desarrollar todas estas ideas. que es lo que hicimos
Es
con
que-
ese modelo membrana.
Es que tengo la intuición desde hace tiempo de que ahí los efectos anarmónicos y también en los amorfos, que es muy parecido,
Claro,
pueden ser importantes. Y esto es que me parece muy interesante, pero
Ya.
tiene pinta de ser mucho trabajo.
claro. O
Por eso te
sea,
preguntaba que si lo puedes hacer tú.
claro, no, es que es mucho trabajo analítico, porque claro, en modelo membrana tuvimos que desarrollar todas las derivadas de todo para, al fin y al cabo, esta minimización la hacemos con una conjugate gradient minimization, es decir, hay que minimizar la energía, hay que tomar todas las derivadas de la energía libre con respecto a tus degrees of freedom. Es claro, eso lo hicimos analíticamente para ese modelo membrana en grafeno. Pero, bueno, modelo membrana en
Lo
general.
tenéis en el paper.
Eso está en el archive desde hace 3 años que, bueno, todos estos efectos de que ahora lo vamos a reenviar porque hemos trabajado, ahora yo creo que está todo mucho más pulido y mucho mejor.
Vale.
Pero ahí están todo el trabajo analítico de derivar. Claro, necesitas hacer eso. Y luego implementar eso en lo que sea.
Hello, I'm how are you?
Ah, okay, nice
Thank you.
to meet you.
Sorry, I'm not aware that you're giving a talk today.
Don't worry. Actually, I think I read the wrong paper because I read the experimental paper.
Yeah, the theory paper is not on archive.
It's not an archive because I read the paper in the archive. And then I was speaking with Santi, and he told me, I think you read the wrong paper. So,
Okay, no worries.
so yeah, I think yeah, sorry for that. So anyway, I will reply saying that I read the wrong, I will read the other paper too, but still the questions that I was asking, I think are,
Yeah, so I think basically, if I remember, they don't really observe the collection of this key point component. So they only observe the collection of
it is very strange. Actually, the first order. But then why did they have a fast? Yeah, that's what we right. So that's I think something first order. But then why?
John, el ordenador, tú. ¿Y esto?
Where are you? You are somewhere here.
yeah.
And then okay, so we are at the CFM basically. You know the CFM, the building in the other side.
Yeah, I'm actually I don't know.
Okay,
I'm not sure.
When did you arrive here or in?
No, I've been here for quite a long time.
A long time already. Okay. Yeah.
I'm associated with this.
¿Esto pertenece aquí?
¿Qué?
¿Esto pertenece aquí?
Yo creo que sí. El mío no es, desde luego.
Lo dejo ahí, o sea. Pero luego sé que lo vayan a robar.
No sé. Ya vendrán a recogerlo, no te preocupes.
Sí, bueno, pero aquí hay mucho.
So I will read your theory paper, okay? But yeah, because I had seen the paper in the archive. So when actually you sent me a draft, I thought that you were referring to the archive paper. I didn't open the.
No,
Sorry, this is my mistake. I will reply back saying that. But still, so it could be first order. There can be a slight first order consequence. And then one is negative one.
Yeah, so basically what we do is actually do the field theory to try to extend that. In ideally speaking, we have two other families. One of the A form, the other one of the A form. Why is that? Think about that.